Okay.
Okay, so the water cycle. So it's composed of different storages and flows. Storage is where the water is stored. So we see water stored in the atmosphere, water stored in the oceans, obviously, in wetlands, in lakes, in ice and snow. And then we also see transfers or flows of water. So we see water flowing from snowmelt down into the rivers. We see water seeping out of the ground into springs. We see water evaporating into the sky or precipitating or raining back down to earth. And then things like evapotranspiration, which is actually water that comes from plants. So as plants photosynthesize, they actually release water. And so that's evapotranspiration. So about 3/4 of Earth's fresh water is stored in glaciers, and a lot of those are being lost to global climate change. So here you can see in just over 60 years, the dramatic change in a glacier. I believe, I'm not exactly sure where this one is. But the major ideas for this topic are that the hydrological cycle, the water cycle, is a system of flows and storages, as we just saw. Those can be disrupted by human activity, as most things on Earth can be. And then we also have the ocean circulation system. This is kind of like the currents that move water around the ocean, sometimes called the ocean conveyor belt. And we'll see how that changes climate and distribution of water. So major ideas: water keeps us alive, obviously, vital resource for all living things. It really helps moderate climates, which we'll look at in detail, shapes the land, as we see, especially in Arizona and Sedona. Water can really be helpful in cleaning and diluting pollutants. Diluting is when you kind of reduce the concentration. So a lot of times you'll use water to kind of wash out things. And then, of course, it moves continuously through that hydrological cycle. Around the world, there's about 1.2 billion people that live in areas that don't really have an adequate water supply. So you can see really high demand in certain areas. And we're going to look a little bit more closely this week at some of those places. Feel free to stop me at any point if you have questions.
Well, no.
So globally, the amount of fresh water that we can use is actually a really tiny percentage. And there's lots of facts and figures here. You don't have to necessarily memorize that 97% is salt water, 3% is fresh water, but you should be familiar with the relative abundances. So I think it's easiest to just look at these images here. So we see in the first one, total global water. We can see that almost all of it is actually oceans. A tiny percentage is fresh water, and then a little bit saline groundwater and saline lakes. Saline actually just means salty, so salty lakes, salty groundwater. Of that 2.5% fresh water, most of it's actually frozen in glaciers and ice caps, so we can't really use that super well. About 30% is available in groundwater. So when we put a well into the ground, usually you're tapping out of groundwater, major source there. And then the rest is surface water and other fresh water. So then you can see the breakdown of that surface water over here. I think the difference between ice and snow and glaciers would be whether they're sort of yearly or whether they exist for multiple years at a time. So ice and snow are obviously seasonal, right? More in the winter, whereas a glacier or an ice cap will actually exist through the summer over multiple years. And the difference between an ice cap and a glacier is just whether or not it moves. Excuse me. Ice cap just stays in one place on the surface, where a glacier actually flows down a mountain, which is really weird to think about, but a glacier is really just a river of ice. It just moves so slowly that we don't really see it. Somewhere like a meter or two a day, I think some glaciers move. And then as we kind of increase with the world's population, that small fraction of Earth's freshwater will become more and more demanded by growing populations. Currently, about 41% of the population lives in river basins that don't have enough fresh water. We live in one of those river basins. Colorado River is currently going lower and lower. So big concern all over the place. Okay, so this understanding is that solar radiation drives the hydrological cycle. That's a really fancy way of saying that the sun powers the water cycle. So insolation, fancy word for sunlight, adds any energy to liquid water, which causes it to evaporate and turn into a gas. So there's the initial driver of the water cycle. As the clouds are in the atmosphere, they get blown around by wind, differential heating, basically. As one area becomes really warm, the air will rise, and then new air has to rush in to fill that space. So that'll move the clouds around, and then eventually they cool and condense and then precipitate or rain down as snow or rain or sleet, hail, etc. But really, without the sun, the water cycle wouldn't happen at all. You can imagine without the sun, everything would just end up on the ground. There would be no more evaporation. Everything would just freeze eventually, obviously, get super cold. Here's a little systems diagram kind of showing storages and flows of the water cycle. So you can see our three storages here, oceans, land, and atmosphere, and then flows going in between each of those with relative volumes of water, 10 to the 15 cubic meters, which is a very, very large number, a lot of zeros. Again, here's some storages from the water cycle. We have organisms, plants and animals, soil, water bodies, including oceans, groundwater or aquifers. This is where water is stored in the ground, so we tap into those for wells. Lakes, rivers, the atmosphere, glaciers, and ice caps. And then we have some flows. I'm actually going to go to this page because it's a little bit easier to read. So this was one of the other assignments in the Google Classroom, just to make find examples of each of these storages and flows in the water cycle. So the flows, again, evaporation is just from liquid to a gas. Transpiration or evapotranspiration is what happens with plants. So they actually combine the two together because they can't really tell. Transpiration is specifically used by the plant, and evaporation is just kind of passes through the plant, and they can't really differentiate which is which, so they just combine them into evapotranspiration. Sublimation, this is when a solid goes directly to a gas. So you'll see sublimation in glaciers and ice caps, places like that. Evaporation, I think, is on here twice because of evapotranspiration. Sorry about that. Condensation, again, just gas to a liquid, like in clouds. We have advection. Advection is just wind movement. So if clouds are blowing through the wind, that's advection, where the wind might blow water across the surface of the ocean or the surface of a lake. Precipitation, again, rain, snow, sleet, hail, etc. Surface runoff. So this is what happens after a rainstorm. You kind of have like, I guess, two major options for the rain, right? The rain's going to hit the ground, and it can do two things. The rain can go into the ground. That is infiltration, when the rain goes into the ground, into infiltrate. And then the other option is that it runs across the ground. So that's what we call surface runoff. So we see a lot of surface runoff here in Arizona because the soils don't absorb a lot of water. So in those big rains, all the water will flow off the surface into streams, into rivers, things like that. So the surface runoff will end up in streams, stream flow, or it'll end up in the ocean eventually and move around with currents. A lot of surface runoff could lead to flooding, right? A river will expand into its floodplain. And then the water that goes underground, as it rains and lands on the soil surface, it infiltrates into the soil surface. And then once it's underground, it will percolate through the soil into aquifers, into groundwater, into big storages like that. So percolate is moving through the ground, moving through soil. It's really sort of weird to think about, but water actually can flow through rocks. So most of the rocks we see in Sedona actually do have water inside of them flowing around. And then that's actually the water that feeds Oak Creek. So that's percolation, moving through soil, through rocks underground. And then freezing, just liquid to ice, liquid to solid, and then melting is solid to liquid. questions on any of those?
Nope.
Okay. Oops. And then we have the ocean circulation system. So this is driven by differences in temperature and salinity, or how salty the water is. So we can see the warmer water here in red, warm shallow water, and then in blue, the cold, salty, and deep water. So this is really driven by an influx of cold, salty water up here in the poles. So as you get more of that cold water coming in, the cold water will sink down and then start flowing around. And then eventually it'll sort of rise up. Basically, as this water sinks down, we have to have water that takes its place, right? So warm water on the surface will move in to take the place of the water that has sunk down. And as this warm water is moving into that place, it kind of creates empty areas over here. So where this water moves out, the cold water moves in to take its place. And continually over here, as this water moves over, the cold water will move up to take its place. So these are like the deep currents. These are actually like a couple hundred meters below the surface. So not actually what we use for ships and everything, but I think in Finding Nemo, maybe they took this with the turtles. So water really plays a huge role in moderating climate. Has a really high heat capacity. That just means it takes a long time to heat up and cool down. So what that means for climate is if you have places like North America and especially Europe, if you look at the latitude here of Britain, if you follow Britain straight across, you'll realize Britain's actually the same latitude as like northern Canada. It's like super cold up here, really frigid. Not a very nice place to live. Whereas Britain, pretty lovely, maybe a little bit rainy, but that's okay. The reason it's so mild here is actually because of this Gulf Stream. So this is called the Gulf Stream because it starts down in the Gulf of Mexico, the Caribbean Sea, brings a lot of warm water from the equator northwards into the northern latitudes. So all this warm water will make the climate a lot more mild than it would be otherwise. And then it will retain all of that heat until it gets all the way over by Europe. And this is actually the reason that Europe is relatively mild, even though it really should be a subarctic climate. Kind of crazy when you actually look at like the latitude, like Germany, I think is like right here, right? So that's like the same latitude as, like no one even lives up here in Canada because it's way too cold. But yeah, that Gulf Stream really plays a huge role in climate.
Yeah.
I think we have 2 more slides. Yep. So upwellings, we looked at those a little bit with the Galapagos. That's just where the cold water comes up, upwells to replace the warm water. That cold water often brings a lot of nutrients to the surface. So you'll usually have really good fisheries in those areas. Lots of good fisheries there. And obviously lots of good fisheries here in the Western Pacific. Some of the biggest fisheries in the world out there. And then downwellings is just the opposite. That's where the warm water moves down to replace the cold water. Yeah, so just kind of a sideways schematic of how it works. The warm water sinks down. The deep currents carry water on the ocean floor from the poles to the equator, and then it replaces the warm water as it moves up. Effectively, you know, if you think about it, without that ocean conveyor belt, most of the heat would just go right to the center of the earth, and there would be very little heat on either end. And of course, it's still colder on the poles, but the conveyor belt really helps to moderate things, make it a lot less extreme than it would be otherwise. And then the last slide is just on the ways that humans use water. So of course, we use it domestically in our houses for drinking and washing and cleaning. Cheers to that. Irrigation is a really fancy word just for using it for crops and farming. So here you can see a canal where they're irrigating their farmland. We use water in industry. We use it for hydroelectric power or electricity. We use it for transportation. Obviously, what was that? The Evergreen or the Even Green, whatever it was, that got stuck in the canal. Big transportation, even to this day, affected economies around the world. And sometimes we use them as boundaries. So this week, we'll start looking more in depth about specific human impacts to water, as well as like different, what's the word? Demand for water around the world. I'm gonna stop this recording.